All right, so I think we're going to go ahead and get started. It is my pleasure to introduce you Mrughank Kashyap. He is a PhD student in ECE and will be defending his thesis today. I have a few things I'd like to say before we get started. Mrughank is the first to defend his thesis in my group at Northeastern. And the journey to get to this point has not been easy. Mrughank has had to survive moving from one university to another. Also, there was a pandemic thrown in there in the middle that certainly didn't help things. But also, Mrughank's thesis is about a topic that is near and dear to my heart because it is something that I studied during my PhD as well, although I studied a completely different aspect of it. So I happen to know firsthand that this is a very difficult, challenging area to work in because in order to study decentralized control, you need to know everything about centralized control, but you also need to know about various adjacent fields, multi-agent systems, distributed optimization. There's a lot of related fields that are adjacent that you need to know about in order to be able to work at the frontier of this field of research. It's been a pleasure to have Mrughank in my group this whole time. I will be sad to see him leave, but I wish him the best, and he will be missed. So I don't want to take up any more of his time. So I will leave the floor to you.
Thank you very much, Lauren, for that kind introduction. To start with, I'm Mrughank, and today I'll be presenting my work on optimal decentralized control with delays. I will start with a few motivating examples. For example, consider a situation where a doctor is performing remote robotic surgery on a patient. So the doctor manipulates a robotic interface on a surgical robot at his end. This generates the commands, which are then transmitted via the internet to an end effector, which actually performs the surgery on the patient. So while performing the surgery, while making an incision, if the end effector encounters a certain obstacle, then the pressure sensors on it transmit that corresponding information back via the internet to the surgical robot so that the doctor can adjust the next set of instructions accordingly. So here, the surgical robot and the end effector have their own respective controllers. And this is a simple example of two agents cooperating with each other to accomplish a common objective. Since information transfer occurs along communication channels, then we have time delays involved in the information transfer process. This could either be due to the time taken by a signal to be transmitted from the surgical robot to the end effector, or maybe due to the processing of that information to get the pertinent data from it. And these delays occur along these dashed arrows. From now on, any system will be represented by the variable G and its corresponding controller by the variable K. So this system controller together can actually be abstracted as the nodes of a directed graph as presented here. But node 1 represents the surgical robot with its own controller, while node 2 represents the end effector with its corresponding controller. And the direction of the information transfer is represented by the directed arrows, and delays occur along these arrows as well. Let's look at another simple example. So here we have a swarm of UAVs that are trying to combat forest fires by maximizing the geographic area of coverage. For example, here we have UAV 1 communicating to UAV 2 and UAV 2 communicating to UAV 4. So again, this configuration can be abstracted as the nodes of a directed graph with the direction of information transfer represented by the directed arrows. And delays occur along these edges. So what is the big challenge associated with such kind of problems? The first problem is each agent or each subsystem that we're considering only has partial information about the overall system. For example, in the UAV case, we saw UAV2 only has partial information about itself and UAV1. It does not have any information about UAV3 or UAV4. Yet it is cooperating with the rest of the UAVs to accomplish a common objective. So this is the notion behind actually decentralized systems. Moving forward, the next challenge is the presence of continuous time delays, which actually increase the problem complexity, because continuous time delays have irrational transfer functions, and they cannot be as easily handled as discrete time delays. The goal of our work is to actually find a globally optimal controller that is subject to this communication and delay constraints that we actually saw earlier in our various motivating examples. So it could mean designing a simple tracker for this robotic surgery problem, where we would like to minimize the tracking error between the prescribed trajectory and the actual trajectory of a surgical instrument for obvious safety reasons. Or it could mean designing a regulator for the swarm of UAVs, where we would like to ensure that the UAVs maintain stable UAV formation in presence of massive wind gusts that could occur during forest fires. Moving forward, I would like to present a brief outline about the rest of the presentation so that we are clear on what exactly we're going to cover in the rest of the talk. So I will start with a brief description of the problem setup on decentralized systems with delays. And then I'll move forward to our first project where we derive the optimal decentralized controller with delays. And before that, we will actually do a simple literature review of previous works done in that field and any adjacent fields. And then we will investigate whether the elegant structural properties that we often associate with the centralized system problem actually get preserved in the decentralized case or not. And then we will see through a simple numerical example our optimal decentralized controller in action. And then we will move on to the second project where we establish robustness guarantees for optimal decentralized controllers. So robustness is a key aspect of controller design because we would like to design controllers that could tolerate and compensate for external disturbances, any planned uncertainties, or modeling deficiencies that could affect the overall system. And more specifically, we'll be studying the stability margins for these kind of controllers. Here, we do not have any delays present in the problem setup. And through a numerical example, we'll see under what conditions exactly these stability margins actually exist. So without further ado, let's start with the problem setup. Again, to reiterate, we are trying to find the globally optimal controller that is subject to communication and delay constraints. Let's look at the figure on the left over here. So here we have agent 1, 2, and 3 communicating in a cyclic manner, and agent 3 is communicating to agent 4. The first assumption that we make over here is that all of these agents are dynamically decoupled. So in essence, they have independent dynamics of each other. For example, in the figure on the left, if a Gaussian disturbance affects agent 1, then that disturbance is not affecting agent 2, 3, or 4. A similar notion exists for the states of each of these agents and for the inputs affecting each of these agents. Following this assumption, let's now try to construct the adjacency matrix of the graph presented on the left. And this adjacency matrix is represented by the term S over here, where the non-zero diagonal elements of the adjacency matrix actually represent the self loops for each of these agents. And any directed arrows that represent information transfer are represented by non-zero elements on the off-diagonal elements. For example, as you can see, agent 1 is communicating to agent 2 on the figure on the left. So we have a non-zero element at this position over here. Similarly, since there is no information transfer from agent 2 to agent 1, we have a 0 in the off-diagonal element over here. Moving forward, let's understand a little bit about the notion of time delays that occur in decentralized systems. There can be propagation delays that occur in such kind of system where the delays occur when a signal is transmitted from the emitter to a receiver. So it depends on the transmission distance of the signal. Or it could be processing delays that could occur when a signal is received by a receiver, then it undergoes some decoding, some signal processing, and some data analysis to extract the pertinent information for actual use. And this is known as, these combined time delays are known as the processing delays. Or it could occur in a related kind of situation where, for example, if we have antenna 1 transmitting information to antenna 2 via a certain node or a certain relay, then the relay is simply bouncing the information received from antenna 1 to antenna 2. So the delay that occurs would be proportional to the total transmission distance between antenna 1 to the relay and then from the relay to the antenna 2. So this is the notion of delays. Now, for the sake of clarity of this presentation, I'll simply be looking at the processing delay case where we have a fixed processing delay tau for all agents, and we do not have any propagation delays, and we have completely instantaneous relays. Now, I would like to stress that we have solved our results. Our results are extremely general in nature, and we have solved the optimal decentralized control problem for any combination of these delays, and this work is present in my thesis. For the sake of clarity, we'll solely be looking at the processing delay scenario right now. Moving forward, based on the fact that we consider instantaneous relays, let's look at the figure on the left over here. So earlier we considered agent 1 is transmitting information to agent 2, and agent 2 is transmitting information to agent 3. So that means agent 2 is simply acting as a relay of any information coming from agent 1 to agent 3. And since we have instantaneous relays, we basically have an implicit communication between agent 1 to agent 3. And this implicit communication is now captured by this red dash arrow presented here. And once we capture all this implicit communication between all of these agents, then we can obtain this augmented graph with this extra red dashed arrows on the left over here. And this is known as the transitive closure of the previous graph that we showed. And accordingly, we modify the adjacency matrix to reflect this new extra implicit communication or information transfer, and we obtain a block lower triangular matrix as shown over here on the right. So our next assumption that we make is our controllers communicate along a known, directed, and transitively closed graph, which is presented here on the left. Finally, we make further simplifying assumption that each controller has a known fixed processing delay of tau. So we make the assumption that any processing delay that might occur for self-information is extremely negligible compared to processing delay that occurs for information received by an agent from another agent. So therefore, we do not have any processing delays along the self loops or the diagonal elements of the adjacency matrix, but we have processing delays along the off-diagonal elements. So based on these assumptions, what does our global controller actually look like? And it looks something like this over here. Our global controller K has the structure of the adjacency matrix that we constructed earlier, and it has no processing delays along the diagonal elements, but it has processing delays along the off-diagonal elements. And this is the global controller that we'll be solving for. Now let's move on and understand the local dynamics that is involved at each of the agents. Let's take the simple example that we considered earlier, the swarm of UAVs, and look specifically at UAV3. So UAV3 is represented by the plant G3, and this G3 will have linear dynamics captured by these two equations. Here X represents the state of a UAV, for example, the position and velocity of the UAV. And this differential equation shows the evolution of that state. Similarly, this equation is known as the measurement equation, where yi represents the measurement of an UAV. So some measurements done by sensors, for example, we measure the height using an altimeter present on a UAV. So this plant G3 is affected by a Gaussian disturbance W3. It has a measurement or output Y3, and it has a control signal or input going into it known as U3. And it receives some information from agent 1, which is its ancestor, and that is delayed by the processing delay of tau. And once it utilizes these two sets of information together, the controller of the UAV3 generates the control signal U3 and transmits some information to agent 4, which is its descendant. So this is what the local dynamics at each of the agent actually looks like. And once we obtain these local dynamics, we aggregate them all together to obtain the global dynamics of the overall system that we're considering. So we aggregate the dynamics together to obtain the global dynamics presented here in this figure, where x dot is equals to ax plus some other terms represents the evolution of the global state of this overall system. So the x is the global state, which is simply a stacking of x1, x2, x3, and x4, all the 4 vectors of the 4 UAVs together. A similar notion exists for the noise vector W and the input vector U and the output vector Y, which are just the aggregation of the 4 vectors together. So we have the global state evolution differential equation, and then we have the global measurement equation. And this is in feedback with a global controller K, which has the structure of the adjacency matrix S. And to reiterate, since we made a simple dynamically decoupled assumption for all the agents, and we are aggregating the local dynamics together. So in that case, the state transition matrix A, the input matrices BW, BU, and the output matrices CY and DYW are actually block diagonal in nature. And finally, Z represents the regulated output of the system. It's a performance measure that we are optimizing for. And we do not make any assumption on the matrix CZ and DZU. So they do not have any special structure and they can be full. So in this case, the states of each of the agents and the inputs of each of the agents are coupled together. And this is actually reflected in the cost function that we'll be optimizing for. Now that we know there are 2 inputs into the system and 2 outputs into the system, we can construct 4 transfer function matrices, where U is the transfer function matrix from W to Z, V is the transfer function matrix from U to Z, W is the matrix from W to Y, and G is from U to Y. And as you know, W and G solely depend on this block diagonal matrices, and hence the transfer function matrices are also block diagonal in structure. While U and V matrices do not have any special structure. So now that we have this global dynamic systems, like in order to solve for the global controller K, we eliminate these 2 signals U and Y to construct the overall closed loop map or the overall transfer function between the signal W to Z. And this transfer function is exactly U plus V K multiplied with I minus GK inverse W. So this is the closed loop map of our system. We are taking the squared edge to norm and minimizing over the variable K, the global controller K, subject to the fact that our controller K has the structure of the adjacency matrix that we assumed earlier. So this is basically a constrained linear quadratic Gaussian problem. Because in the standard linear quadratic Gaussian problem, we simply do not have this structural constraint on the global controller K. Moving forward, let's jump to the results of our first project. We will start with a brief literature overview of centralized systems and adjacent works and delays before we proceed to our results. Let's begin with the well-known centralized linear quadratic Gaussian case. So here we are considering a single agent G, which is in feedback with a controller K. It has a measurement Y and a control input U. So in this case, the optimal control policy is linear, and we have a closed form solution for the global optimal controller. And the fact is, this controller K has an elegant observer-regulator separation structure shown on the right over here. So here, the observer is a Kalman filter, where L represents the Kalman gain, T represents the observer dynamics, BU is the input matrix, and F represents the LQR gain. So our observer is making a prediction of the state of the plant G. So this is a very well-studied problem, and this work has existed since the 1960s. And the fact is, this type of controller, the solution for this controller, it's like extremely efficiently computable. Because we do not have to resort to any numerical techniques, we have to solve for 2 algebraic Riccati equations. So these are all the elegant properties of the centralized LQG system. So now that we know the elegant properties of centralized LQG system, which is presented here on the left, and we discussed it in the earlier slide, the big question is, for a general decentralized LQG system, do we have all these elegant properties? Or is something else happens over here. The fact is, if we are studying a completely general decentralized LQG system, for example, if we impose a structural constraint on the controller K, then there need not be any linear optimal control policy. And in fact, Witzenhausen in 1968 showed that for a simple two-agent system. And the fact is, these kind of problems are extremely hard to solve. And there is a plethora of literature on trying to solve general decentralized LQG problems using various numerical techniques. And the other aspect to remember in a general decentralized LQG case is that none of these structural properties that we saw, none of these elegant properties that we saw in the centralized LQG case are transferable to the decentralized LQG case. So there has been study of several special cases of decentralized LQG system by making assumptions on the plan structures and assumptions on the information sharing pattern. For example, Ho and Chu in 1972 showed that an optimal controller is linear if we have a partially nested information sharing pattern. And Rodkois and Lal in 2002 established the notion of quadratic invariance, which is used for solving for this linear optimal controller by casting it as a simple convex optimization problem. And note that this convex optimization problem is still infinite dimensional, and we can actually use numerical techniques like vectorization to solve for the controller to arbitrary accuracy. And there has been a lot of literature in that area as well. Moving forward, Kim and Lal in 2015 studied a special kind of decentralized systems known as dynamically decoupled systems, where they leverage the structure of these kind of systems to split the global controller synthesis problem into separate centralized LQG problems. So we saw the constrained LQG problem earlier. They were able to leverage the structure of dynamically decoupled systems to separate them out into smaller problems. And since these are centralized LQG problems, we no longer have to resort to numerical techniques. We can solve them using modified algebraic Riccati equations. Now, let's understand the notion of delays in centralized LQG. And this work was done by Merkin in 2011 and 12. And it is actually the basic building block on which our work is based. So here we have a plant P with a noise vector W affecting the system and a regulated output Z. And this plant P is in feedback with a controller Q with a control input U. And the control channel is actually delayed in such a way that one of the channels of the control channel is undelayed, where the other is delayed by a processing delay of time. So this is also known as an Adobe delay problem. So Merkin studied this problem. And the important fact to remember here is we are now dealing with continuous time delays. So this transfer function is irrational. If we had a discrete time delay here, we could actually merge this delay into the plant and solve for the controller easily. But now that we have an irrational transfer function, Merkin used a simple loop shifting technique to actually cast this delayed centralized LQG problem as a combination of FIR blocks and a non-delayed centralized LQG problem. So here we have a plant P tilde, which is a simple transformation of the plant P, and it's a finite dimensional plant. And then it's in feedback with a controller K tilde, which has a bijective relation with the original controller K. And we have an FIR block delta and an FIR block psi over here, and two FIR blocks pi u and pi b present as well. And interestingly, this FIR block delta and psi are orthogonal to each other, and the psi block is actually inner, so it is energy preserving. And this is reflected in the cost function that we'll try to optimize. So here on the left-hand side, we have the cost function for the centralized LQG with delays. As you can see, the delayed the lambda m is actually reflected within the cost function. And we can actually cast using this loop shifting technique, convert this cost function into a combination of an FIR block and a centralized non-delayed LQG problem cost function. And once we solve for the K tilde on the left over here, we can use the bijective transformation to recover the controller K.
And so, there are no delays in the lower part of this block diagram, right? So those green boxes, there are no delays there, right?
No, these are just FIR blocks, actually.
Yeah. And delays are in the delta and the psi.
So they are also FIR blocks. So all the blocks presented in green over here on the figure on the left, on the right, FIR blocks, finite impulse response blocks. So that is the interesting result by Merkin, where he was able to handle continuous time delays without resorting to any delay approximations like Paddy approximations or discretizations. And this will be the basis of our work for decentralized LQG with delays. To understand the context of our work a little bit better, so I am presenting this slide here. So we know centralized LQG without delays is an extremely well-studied problem since the 1960s, and there is a plethora of work in this area. Centralized LQG with delays was studied by Merkin in 2011 and 12, where he was able to handle continuous time delays without resorting to any approximations. Decentralized LQG without delays was studied by Kim and Lal in 2012 and 2015, where they handle dynamically decoupled systems. And our current work, my current thesis, actually covers this fourth quadrant here, where we studied the decentralized LQG with delays. And an important fact to note over here is we are generalizing these three previous results because these are simply special cases of these are simply special cases of our current work. I would like to state that Cristalli and Cho in 2012 and 13 actually studied the two-agent LQG problem with delays, and especially they actually solved the surgical robotic problem earlier. Moving forward, let's look at the main results of the work that is present in our thesis. So to start with, we'll understand the roadmap of the solution process. Let's look how we solve the centralized LQG problem. So here on the left, we have the optimization problem for a centralized LQG case. Notice we do not have any structural constraint on the controller K. So we use the ULAP parameterization to actually cast this non-convex optimization problem as a convex optimization problem in terms of the parameter Q on the left, on the right. Now that we know this is the process to solve a centralized LQG problem, can we actually use a similar procedure for the decentralized LQG problem? So we will study that by looking at a simple two-agent example. So here we have agent 1 transmitting information to agent 2. And we have an adjacency matrix S as presented here on the bottom right. And the global controller K has the structure of this adjacency matrix with a processing delay of tau along the off-diagonal element. And since our agents are dynamically decoupled in nature, our W and G matrices are block diagonal as we consider in our assumptions. So following this, let's look at the roadmap of the solution process for a decentralized LQG problem. So we started with the constrained LQG problem that we saw earlier. We have the structural constraint on the global controller K. Now, once we have that, we utilize the notion of transitive closure to prove quadratic invariance established by Rothfuss and Lal in 2002. And once we have proved that, we can leverage the Euler parameterization again to cast this non-convex optimization problem as a convex optimization problem. To cast it as a convex optimization problem in terms of the parameter Q. And next, we use the dynamically decoupled nature of our systems to separate out this global convex optimization problem into n separate optimization problems. In fact, the separation occurs along the columns of the parameter Q. So one of the optimization problems here would be solving for one of the columns for Q. Now, once we have this kind of setup, as you can see, we still have a continuous time delays in the Q parameter. So we can leverage Merkin's result in the third step to cast this n centralized delayed LQG problems into n non-delayed centralized LQG problems. And this is how we do. For example, we look at the column 1 of the parameter Q. We can separate out the Adobe delay matrix as presented here, and then we can use the loop shifting transformation to obtain this new convex optimization plot. And once we solve for this parameter Q tilde on the bottom right, we can retrace our steps backwards to obtain the global controller K. This is the roadmap of the solution process. Now let's look at the key and more interesting results of this global controller K. So we know the centralized LQG has an elegant observer-regulator separation structure, and it is often the principle that is used in controller design today. So what happens in the decentralized LQG case with delays? And the fact is we have a similar observer-regulator separation structure, as we can see in the figure on the right over here. Here, our agent, at the agent level, we have the plant BI, and it has a measurement, it produces a measurement YI that goes into the controller. It receives some information from its ancestor, which is delayed by a processing delay of tau. And then once both these sets of information are processed, then we can generate the control signal UI present here. So what happens when the measurement is sent into the controller? It is multiplied with a certain Kalman gain Li, and then with an observer dynamics TII bar. And interestingly, now each agent takes into account the dynamics of all its descendants as well within this observer dynamics. And then it is multiplied with a modified LQR gain, which is obtained by solving a modified algebraic Riccati equation. And here, as stated before, the pi UI and the pi BI represent two FIR blocks. And we are transmitting some information to our descendants as well. And here the E blocks actually represent a combination of the columns of an identity matrix. And all they do is either zero pad a certain vector or truncate a certain vector. That's their only function in this diagram. So notice that our controller is actually a combination of delay independent and delay dependent blocks. So it is extremely easy to tune such controllers when the value of the delay changes, and we no longer have to recompute the controller all over again for different value of delays. Further, our controller is extremely easy to compute because we are now relying on solving two algebraic Riccati equation, albeit they are modified a bit to take into account the new framework. Now that we have this decentralized LQG setup with delays, what happens when we have tau is equals to 0 or when we have no delays? So in that case, the pi U block becomes an identity matrix and the pi BI block becomes 0. And this is what our new controller for a non-delayed case actually looks like. We still have the observer regulator separation structure, and we no longer have a dependence on the delay. And as stated earlier, the pi BI block becomes a 0 and the pi UI becomes an identity. So we recover the results of Kim and Lal that was published in 2015. So to put our work in, to understand our work a little bit better, let's look at the local controller through the two-agent example that we considered earlier. So we have agent 1 here that has a measurement Y1, and it is transmitting some information to its descendants, nu1, 1 and nu1, 2. And it generates the control signal U1. So here we have the measurement Y1 that is multiplied by a Kalman gain. So note that this Kalman gain is not dependent on delays. So the observer gain actually does not change in this kind of framework. And then we have the observer dynamics that takes into account the dynamics of agent 2 as well. And that is multiplied with a modified LQR gain F tilde 1. And then we have the two FIR blocks pi U1 and pi B1. And then accordingly, we generate the control signal U1 and transmit certain information to our second agent. So what does the second agent do when it receives this information? It receives this full information, but utilizes only the second set of information, which it delays by a processing delay of tau. And as before, it has its own measurement Y2 and a control signal U2. So it processes its own measurement Y2, multiplying it with a Kalman gain, an observer dynamic, an LQR gain F2, and then it sums the information that is received from agent 1 with its own predictions and generates the control signal U2. This is what the local controller at both the agent looks like. And as to state, we still have the observer-regulator separation structure as mentioned earlier. Sorry. To put our work into further context, we know that centralized LQG without delays has this familiar observer-regulator separation structure. And then we have Merkin's result where he was able to handle delays without resorting to any approximations. And then we have Kim and Law's result where they handle dynamically decoupled systems for stable plans. And finally, we were able to generalize all these cases together and solve for the decentralized LQG with delays. And as you can see, if tau is equals to 0, we recover the first quadrant, Kim and Law's result. If we are dealing with simply a single agent with delays, then we recover Merkin's result. And if we are dealing with a single agent with no delays, then we recover the standard centralized LQG without delays. So our work is a special case of all these three previous results that has been studied before. So moving forward, let's look at our optimal controller in action. So we have here 4 agents, and they're all in open loop, and they're represented by this second order differential equation. So in fact, they are lightly damped oscillators. And so here they have 2 states. One is the position state, the other is the velocity state. And we are starting from completely different position state, but we have the same initial velocity state. So if we are running all these 4 systems in open loop, so the plot for our position versus time actually looks something like this, where all of them are oscillating, but in a lightly damped manner. As you can see, we have a slight reduction in amplitude as we go forward in time. Now let's add in a control signal here, but UI. But in this case, we still have complete decentralization. So in a way, none of these controllers are communicating with each other. So we have a new cost function J, where our goal is to synchronize the position states of all these 4 oscillators. So in the cost function, we are penalizing the difference between the position states for each of these agents, and we have a weighting factor of 0.02, and we are also penalizing the control input. And as you can see in this case, the position states actually start from different values, but they all converge to 0. And intuitively, this makes sense because none of the controllers are communicating with each other. So the best way to synchronize is to drive all their states to 0 and just remain there. And this is what happens in the plot as we saw. Moving forward, let's look at a more substantial decentralized case, and this work has been published in our archive paper that has also been submitted to IEEE Transactions in Automatic Control. Here we have the same diamond network configuration that we saw earlier for the UAV swap. So in this case, again, we have the same cost function, and we would like to synchronize the position states. And once we implemented our decentralized controller, as you can see in the position versus time plot, all the positions start from different initial values, but they start synchronizing at the value of around 25 seconds. And further on, they remain synchronized. So this is our optimal decentralized controller in action. Then we ran the first experiment where we tried to determine the average optimal cost for this network configuration. So on the y-axis here, we have the average optimal cost for the diamond pattern, with the x-axis showing the variation in delays. I'd like to stress here that here the average optimal cost has not been computed numerically. In fact, we derived a closed form expression for that average optimal cost. And then we determine the requisite cost for this network configuration. And as you can see, for the diamond shaped pattern, it starts from around 2.28 and starts saturating to about 2.34. Now we varied the different network configurations in which these agents can communicate with each other. And we looked at 9 different configurations, including the diamond shaped pattern. So this is the plot for the average optimal cost versus the variation in delays. And we have 9 different configurations where the red arrow represents fully disconnected controllers. So there is no communication between them. While the black represents fully connected controllers, because all these agents are communicating in a cyclic manner. And by the notion of transitive closure, each of them is communicating with every other agent. So let's look at delay is equals to 0. So in this case, just on the y-axis, as you can see, the least amount of cost is expended for the fully connected case, while the highest is for the fully disconnected case. And as we increase the amount of decentralization, well, the average optimal cost starts increasing. And intuitively, it kind of makes sense, because if we have a common objective, if we have a given objective, the more the amount of information we have about the overall system, we'll be expending the least amount of cost to accomplish that, compared to a case where we have less amount of information about the overall system. Next, let's look at a case when we vary the value of delay. So we start from 0 value of delay to a value of 16 seconds. And as we can see, all these plots start for different network configuration actually start converging towards the case where we have the fully disconnected case. And intuitively, this also makes sense, because as we increase the value of the delays, the amount of pertinent information at a given time instant for a single agent is reduced compared to a case where we have less value of delay. And therefore, we are converging towards a case where we have no delays and no links between the different controllers. So this work was also published in our archive paper. And with these results, I would like to move on to our second project, where we study the robustness guarantees for optimal decentralized controllers. I would like to reiterate, robustness is an important aspect of controller synthesis, because we would like to design a controller that can tolerate external disturbances or modeling uncertainties that could affect the system and still keep the closed loop system stable. We'll look at the stability margins for the optimal decentralized controller. Let's start with something that we know, a simple literature review of centralized linear quadratic regulators. I'd like to state here that in this case, we have a plant G, and we are directly observing the state X, the plant G, and we are considering a single input, single output system. So the plant state X and the control signal U are scalars. And we are solving for the given cost function here on the right, where Q and R matrices are designed by the control designer. And in this single input, single output case, we have a static controller F, and this control policy is linear. This is a well-known problem and a well-studied problem in centralized control literature. And we know for these centralized LQRKs, the gain margin K actually varies from 0.5 to infinity, and the phase margin varies from -60 degrees to 60 degrees. So what do these gain margins and phase margins actually mean? So one way to interpret is that, this gain margins and phase margins is that, imagine we have a multiplicative uncertainty delta that is affecting this input channel U. So if we have a value of K over here for the gain margin, delta is equals to K, then if the K value varies from 0.5 to infinity, our overall closed loop system still remains stable. If it goes below the value of 0.5, then we have instability, we have an unstable closed loop system. Similarly, for the phase margin, if delta is like the value of the phase lag or the lead actually that can make the closed loop system stable only lies between -60 degrees to a value of 60 degrees. Otherwise, our system actually becomes unstable. And this form of interpretation of gain margin and phase margins were introduced by Safanova and Athans in 1977 and Letomati et al. In 1981. Now let's look at a more complicated case. Let's look at the multi-input, multi-output centralized LQR case. In this case, the state X and the control signal U are vectors. They're no longer scalars. For example, for a two-input, two-output case, we have for a two-input and a two-output case, we have a 2x2 static controller F. And the fact is, if we independently perturb each of these input channels, then we have a gain margin of 0.5 to infinity and a phase margin of -60 to 60 degrees independently for these channels. And the fact is, these guaranteed stability margins, the gain margin and the phase margin, exist if our cost matrix R is diagonal. And there is a famous counterexample by Letomaki in his paper where he showed that if the cost matrix R is not diagonal, then this guaranteed stability margins can become arbitrarily small. So they no longer exist. Now let's look at the stability margins for centralized linear quadratic Gaussian case. Here we have an output feedback. So we are no longer observing directly the planned state X. We are measuring a noisy version of the planned state X in the form of Y. So our controller in this case is dynamic in nature. What do we mean by a dynamic controller? So the controller has an observer, regulator separation structure that we discussed earlier. So with this observer, you have this observer dynamics where it tries to predict, where it actually predicts the planned, where it tries to predict an estimate of the planned state X. So this is what makes a controller dynamic. And our LQG, centralized LQG, is obviously dynamic. And there is a famous counterexample by Doyle in 1978, where he showed that there are no guaranteed stability margins for this case. Now let's recap the work on decentralized LQR by Shah and Perillo and Swigat and Lal. So I would like to stress over here that our problem setting has changed substantially from our previous project that we presented earlier. And I will stress where the problem settings has changed in my brief description now. So we have planned G here, and we are directly observing the planned state X. So we have, for example, in the two-agent case, we are observing X1 and X2, the states of agent 1 and agent 2. So in comparison to project 1, we were dealing with a linear quadratic Gaussian case or an output feedback case. So in this case, now we are directly observing the planned state X. That is one key difference from the previous setup. And the fact is, based on this transitive closure based on the transitive closure graph of this kind of system, our controller K has the structure of the adjacency matrix S. And it follows the information sharing pattern of this two-agent system. And to reiterate, our planned G also has the structure of the adjacency matrix S. So because our planned G has the structure of the adjacency matrix S, we can actually consider our state transition matrix S2 also having the structure of S, and similarly the input matrices also having the structure S. And this is a critical difference from our previous project setup that we considered. We are no longer considering dynamically decoupled systems. So we do have some form of dynamic coupling, provided the structure of the plant also satisfies the structure of the adjacency matrices. Now, in this kind of setup, we have a decentralized LQR. It's state feedback based, like centralized LQR. But the fact is, centralized LQG, but the fact is, just like centralized LQG, it has a dynamic controller, as you can see, because this decentralized LQR controller tries to make a prediction of the state of agent 2. So it has a dynamic component to its structure. So the big question is, if we perturb each of the inputs to agent 1 and agent 2, can we actually have a similar gain margin, phase margin, or a similar stability margin concept for this kind of decentralized LQR setup? And the answer is actually a conditional yes. So this work was published in our recent paper in IEEE Control System Letters, where we showed that if we independently perturb the inputs U1 and U2, then we will have a gain margin of 0.5 to infinity and a phase margin of -60 to 60 degrees if our input matrix BU, which is represented here in the global equation, global state differential equation, and the input cost matrix R are block diagonal in nature. So only if these two matrices are block diagonal, we will have guaranteed stability margin, just like centralized LQR. And what happens if we violate those conditions, then we'll show that result in a simple numerical counterexample that is also included in our paper. So we consider the two-agent case. Each of the agents has a single input, single output, and a single state. And the global state vector X has the following formulation, where our state transition matrix A has the structure of the adjacency matrix S. And our input matrix BU is represented here. It has the structure of the adjacency matrix S, but the beta parameter over here determines whether it is diagonal or not. And similarly, we choose the cost matrices Q and R, but the rho parameter within the R matrix determines whether the matrix R is block diagonal in nature. We ran 2 experiments. In the first experiment, we considered R to be block diagonal, so the rho value was equals to 0, but beta was not. Here, we present a plot of the gain margin in dB along the x-axis, and the value of the beta along the gain margin in dB along the y-axis, and the value of the beta in the x-axis. So in this case, as you can see, if we have a value of beta at -50, then we have a gain margin from around -14 dB to infinity. So this is what our gain margin plot over here represents. So the blue shaded region represents stable regions. So it kind of corresponds to when we have a stable closed loop system, while the orange region represents unstable, when we have unstable closed loop system. And this black dashed line represents the -60 dB line, which corresponds to a gain value of 0.5. And as you can see, we already assumed rho is equals to 0 because R is block diagonal. And if our beta value is actually equals to 0, we get our standard gain margin of around 0.5 to infinity. So we recover the result of the centralized LQR case. And if we have variation in the value of beta, we have a severe deterioration in the value of the gain margins that we saw. Moving forward, in the second experiment, we considered R to be non-block diagonal, while our input matrix VU is block diagonal. So the value of beta is now equals to 0, while rho is non-zero. So again, we have the same plot with the x-axis being the variation in the value of the rho. And as you can see, if rho is equals to 0 and beta is already equals to 0 because VU is block diagonal, we recover the centralized LQR gain margin of 0.5 to infinity. But in other cases, when the value of the rho varies, then we have a severe deterioration in the value of the gain margins. With this, I would like to move forward to summarize our contributions today. In our first project, we obtained the closed form solution of the optimal decentralized LQG controller in presence of delays. And we observed that it has a familiar observer regulation separation structure. And the fact is this optimal controller is efficiently computable because we can solve it using algebraic Riccati equations. We obtained the closed form expression for the average optimal cost and numerically validated the performance of our decentralized controller for different values of delays and for different network configurations. Finally, in our second project, we studied the robustness guarantees for optimal decentralized LQR, where we established guaranteed stability margins for this optimal decentralized LQR controllers. Here, we did not consider any delays. And these guaranteed stability margins exist if our input matrix VU and the input cost matrix R are block diagonal in nature. With this, I would like to present a summary of our references that have been where our work has been published. So in IEEE CTC 2019, we solved the optimal decentralized controller without delays for stable plans. In CTC 2020, we published the work on optimal decentralized controller with processing delays for stable plans. And in our archive paper, which has been submitted for review under transactions in automatic control, we generalized all the previous works together and determined the optimal decentralized controller regardless of plan stability. And we considered all possible combinations of delays. And in this work also, we actually parameterized all stabilizing controllers. I did not provide the work in this talk over here, but that is also a significant level of work that has been published there. And in the final paper, which has been published recently in Control System Letters, we studied the guaranteed stability margins for decentralized LQR. And then we established under which conditions these margins are going to hold and under which conditions they are not. With this, I would like to acknowledge a few other people who helped me through the PhD journey, my parents, my in-laws, my wife, and my younger brother, and of course, my lab mates, who have been very instrumental. and throughout my PhD journey. And thanks to Lauren for guiding me through all these 6 years and keeping me sane. And thanks to the audience for being so wonderful and for your patience, and I'd be happy to take any questions.
Yes, we can take some questions from the audience, or also if there's any questions online. I don't know that anybody wants to ask. If anybody has questions that they want to ask in the chat, or I guess they can feel free to unmute themselves. If they want to speak that way. So are there any questions in the room?
Hey, Laurent, Mario here, and I apologize for joining later. So I have 1 or 2 questions. Firstly, congrats to Muranka for, that was a wonderful presentation and all the papers. Just out of curiosity, if you ask me to control a system with a time delay, standard practice is to use a Smith predictor, right?
Yeah.
So how does your explicit solution compare to sort of something naive where I would use a Smith predictor for each agent and then do the non-delay case? That's
okay. So first to state, actually, so let's move back to the slide on Merkin's result. So yeah, so in Merkin's result, he actually he handled this Adobe delay case. And so to start with, the Smith predictor, as far as I know, is able to handle a dead time delay case when.
Sorry, Mario won't see the red pointer, so maybe you can use a mouse.
Oh, okay. Yeah, thank you.
Yeah.
So here we have this problem. So you mentioned the Smith predictor. So the fact is, as far as I know, the Smith predictor is able to handle delays when both the input channels are actually delayed. And one of the important aspects to remember here is Merkin's result is actually a modified version of the Smith predictor. In the Smith predictor, we have this internal feedback pi b, which exists actually. And in the results provided by Merkin, this pi b actually is similar to what we obtained for a Smith predictor. Like the way we define the Smith predictor, the pi b actually looks exactly like that, with a slight difference in like conditions that we are considering. This pi u block that we see, this new FIR block, is a new feed-forward term. And what it does is it separates out the effect of this delayed channel from the undelayed channel that would affect the regulated output C. That is the extra purpose of this pi u block. To reiterate, so like the Smith, if you consider a dead time delay case where both the channels are delayed, then we do not have this pi u block, and we actually recover the Smith predictor result. And this is a modified version of the Smith predictor that Merkin studied. And in fact, he writes it in his paper. He compares both the cases together, and he shows that, okay, if I actually remove this Adobe delay case and solve the dead time delay case, the pi u becomes an identity matrix, and the pi b actually tends to the Smith predictor, is equivalent to the Smith predictor version.
Well,
So
along those lines, then in pi b, there must be a delay term, right?
So yeah, so we have in pi b actually looks like the difference between two LTI system in which one of the LTI system is delayed.
Okay, because initially I asked you said there's no delay there, but there is a delay there.
Yeah, but it's kind of an FIR block, right? So now not because we are like a different, like taking a difference of two different systems. So one is a system that is by itself, so it's generating a signal yi. The other is a delayed version of that system, and we are subtracting those two signals together.
Exactly. Like 1 minus exponential, there must be something like that.
Yes.
Okay, okay, good. Otherwise, you won't have infinite dimensionality.
Yeah.
Right? So, okay, all right.
Yeah.
Fine.
Okay.
right. Thanks. That was a very good answer. And I have a question regarding the second portion of your thesis. I mean, when you're talking about gain and phase margins, yeah, that's what we teach our undergrad students, but they are not really something that we should rely on, right? Because the gain margin assumes that the phase doesn't change at all and that you're changing a single gain in your system, right? And phase margin, you keep your gains and then you change your phase. But typically, sometimes you have perturbation both in gain and phase, right?
Yes, that's
So,
right.
I mean, your results are very, very interesting. I was wondering what happens if you actually consider perturbation in both. In other words, if you look at the H infinity norm of the points where the perturbation enters, or if you do a mu analysis type, do you still recover the same margins that you had for the LQR?
Yeah, so that is actually a good question. So to answer in a short way, like that brings up the concept of disk margins that has been recently studied, where you can have variations in gain and phase, and then the concept of using H infinity control. But that is something that is actually a future work that can be considered to take this work forward. So to answer frankly, we actually did not study a complete like when we have like a change in both the gain and the phase almost simultaneously, because we did not have much of a time, because it was even independently when we perturb gain and just the gain and just the phase, we kind of like during the solution process, we kind of thought that, okay, we do not have any guaranteed stability margins because it's a dynamic controller. And we never got to the part to study when both of them are simultaneously changing. So to answer your questions, I do not have a specific, I cannot give you a specific result, because already the simple gain margin and phase margin cases were extremely difficult to understand because of the way the system setup is, because we have a state feedback system, but yet we have a dynamic controller. And we actually thought that there would be no guaranteed stability margin. And then we identified that, okay, we have certain stability margin, like certain gain margin and phase margin. So yeah, so that is definitely the next step to study, actually, to understand the notion of disk margin, to understand better concepts of stability margins for decentralized LQR, when both the gain and phase are actually varying simultaneously. So yeah, hopefully that answers your question.
Okay, thanks. No, I just was wondering, I know it's way beyond the scope of the thesis. I was just wondering if you did some experiments, numerical experiments, to get an intuition of this, but anyway, thanks for answering.
There any other questions from the audience or from online? Looked like it. So I think this will conclude the public portion of the defense. So let's thank Ragank again. And, from this point forward, I would like to ask everybody that is not part of the committee to please leave the room and to please leave the Zoom as well. And we will be doing the closed door part of the session starting now.